Alright, ladies and gentlemen, today we're going to go over lecture 1.2, the development of atomic theory. We're going to focus on 4 great thinkers of our era and their experiments. We're going to use them as a timeline to understand the development of the atomic model. First things first, a nice little graphic organizer for our thoughts. This right here will go over Democritus, Dalton, Thomson, Rutherford, and Bohr, some key points about their experiments, and some nice ways to remember what they did. If you want to look at a more linear view of atomic theory, this is a nice little timeline that I stole from another teacher. Always got to keep those resources going. So Democritus, let's talk about Democritus first and foremost. He is essentially the father of atomic principle. And what he thought is that everything in the world is composed of atoms. Everything in the world is composed of atoms, but these atoms determine structure and they're constantly moving by how they're shaped. So if they're hooked atoms, they hook together and form solids. If they're water atoms, they're slippery and wet. It was mainly debunked by people like Aristotle because they wanted to know how the atoms started in motion. A solid question. A good way I remember Democritus is a crying demon, Democritus. You get the picture. And I kind of remember his model by the earth, wind, fire, and water idea that all atoms are made out of earth, wind, fire, and water. Kind of just the way he thought of water molecules being slippery and wet and whatnot. Next up we have Dalton. And Dalton's model of the atom was single indivisible units. Now, Dalton essentially thought that all these little tiny spherical rock-like things made up the entire universe. And he is the first one to really propose the atom as it is, as we think of it today. Now, I remember Dalton. It's a nice little mnemonic to help you remember Dalton. And some little rocks, just to keep that going. We have J.J. Thomson. And J.J. Thomson is the first real experimenter of atomic principle. And essentially, he discovered subatomic particles in 1896. And I'll show you exactly what he did. Think of the principle of magnets. Positives and negatives get sucked together. Oops, excuse me. Once again, let's think of some magnets. Positives and negatives, when they come together, they're attracted in the same sense. But if you put 2 positives together, they push each other away. And if you put 2 negatives together, they also push each other away. So Thomson took that into his experiment, the cathode ray tube. This right here is the cathode ray tube. He hooked up a battery to a big tube and it shot a beam of lasers right through the middle. Now, he didn't know what that beam was made out of, so he had a clever little thing that he did. He essentially ran a voltage through the cathode ray tube and attached a battery to the top of the cathode. And he saw the beam form. Now, when he put the battery on top of the cathode ray tube, the beam actually bent towards the positive magnet and away from the negative magnet. Now, this tells us something, but I want you to stop and think for a second. What subatomic particle did he discover, given that we have a positive charge up here, and we have a beam of subatomic particles that go towards, they bend towards the positive charge? Take a second, pause the video, think of what subatomic particle he could have discovered, and go ahead and give this video a watch. He discovered the electron. However, he did not discover where the electron was. He just knew that the beam must be made of negatively charged particles that had 1/2000th the mass of a normal hydrogen atom. And so he assumed that had to be the electron. Now, he proposed that all these electrons were floating in this blob of positive charge, and he called this the plum pudding model. Now, unfortunately for him, that was wrong. How I remember Thomson is Chomp's son is like Thompson, and he was like the electron boy with the what's up pudding cup. Thomson discovered the electrons so that atoms were like little wads of plum pudding with negatives thrown about. An interesting model, but he would actually have a student come later on and disprove him. So go ahead and summarize what Thomson did for a minute. Pause the video, take down your notes. 3 to 4 sentences describing Democritus, Dalton, and Thomson. How they discovered what they discovered and what they discovered. Up next we have my dear friend Ernest Rutherford. And he was actually a student of Thomson. He took Thomson's ideas and said, I'm going to change it up a little bit. And he used a gold foil experiment where he fired these little alpha particles at this gold foil. Now, Here's exactly what it looked like. Here's his little radioactive source, which is firing those alpha particles straight at the gold foil. And most of them are passing right through. But every now and then, one of these particles will hit the gold foil, pink, bounce to the side, or bounce right back. Now, this was very confusing because he expected all of these super high speed, basically little miniature missiles to fly right through the gold foil and hit the other side. This is a bigger picture of what it looks like. The alpha particle emitter goes right through the gold foil almost all the time. But every now and then, it'll deflect off or even bounce back. So go ahead and look at Rutherford's data right here and take a hypothesis about what this means. 98% of the particles went straight through the foil. 2% hit the foil but zoomed off in a different direction. And a tiny, tiny amount of them, about 1 in every 2,000, about 0.01%, hit the gold foil and bounced right back. Rutherford said that it was almost as if you had fired a 15-inch shell into a piece of tissue paper and it came back and hit you. Kind of crazy. Take a second if you get a chance to watch this video as well. It's phenomenal. Once again, here is his experiment. And here's what his data meant. Most of the alpha particles went straight through the atom because it's mostly composed of empty space. And this is extremely important. You have to know that the atom is mostly empty space. Now, some of the alpha particles deflected because they came really close to the electrons and zoomed off. Every now and then, that one that would hit the gold foil and bounce right back was hitting the small but very dense, positively charged nucleus. And that's how we discovered the nucleus. So you see in here a beam of alpha particles would fire, and almost every time they would go right through the gold foil atoms, because the gold foil atoms are composed of mostly nothing, mostly just empty space in between the nucleus where all the protons are and the electrons. Now every now and then one would hit that very small nucleus and bounce right back, because we know the nucleus has all the protons and neutrons in it, making it positively charged and full of stuff. So bink, fired right back. Here we have what the plum pudding model would suppose that alpha particles would do when they were fired through it. And here we have a more modern set, what Rutherford proposed, that there's the atomic nucleus in the middle, bink, and most of the atom is just empty space. Remember, the atom is mostly empty space. This is important point number 1. Important point number 2 is that the atom has a very small but very dense nucleus. And all the alpha particles that bounced back, bink, came right back, were coming into contact with a positively charged nucleus. Here's how I remember Rutherford. A rudder, like the rudder on a boat, plus Ford the truck, and he discovered the nucleus like a big nuclear explosion with the gold foil experiment. All gold, everything. And he had a more modern model of the atom. But we don't stop there. In fact, the last guy we want to talk about, Niels Bohr, refined Rutherford's model by using electricity and hydrogen gas. Now, you guys have seen things like this before. If you ever think about neon signs, they light up when you plug them into the wall, when you shoot electricity through them. The reason why is because Bohr knew that firing electricity through gas produced visible light, what we call emission. And we can see them on an emission spectrum. He saw pink, blue, green, and red. But he saw specific colors. And he said, wait a minute. I know that shooting electricity through hydrogen excites these electrons, but the colors only produced for a few of them. Why aren't all the colors lighting up? And he said if the electrons were free to roam all over the place, then we'd get all sorts of colors. However, given that we only had a few, Bohr proposed that all of the electrons actually exist in little orbitals. Just like planets revolving around the sun, electrons sort of revolve around the nucleus. Now, this isn't the full idea of how it works, but this is a good way to think about it. We call this electrons restricting to orbitals or energy levels. And we get excitement of electrons And Bohr, the Nile River plus Bohr, as we remember Niels Bohr. And he said the electrons orbit in specific rings called orbitals, just like Saturn, the rings around Saturn. And we have the modern model of the atom. Dalton's atom turned into Thomson's electrons, plus Rutherford's empty space in the nucleus right in the middle, and then Bohr's energy levels. And we have what's known as the modern day atomic principle. So go ahead and summarize that for me, and give this exit ticket a shot to see how well you understand the development of atomic theory. Good luck. Hope this helps.